Let's build a neural network and optimize it by adjusting its weights using random numbers. I'm going to use Cloud 4.5 Haiku and let's build this from scratch. It'll be an interesting experience. Please build a neural network using PyTorch, but we will only be doing a forward pass. We will not be doing back propagation or gradient descent. We will adjust the weights of this neural network just by using random numbers. So this will go on iteratively, have a max iteration variable. Also, variables at the top for the size of the neural network. I can specify the training data set for this will be 2-digit by 2-digit addition problems. And the print statements should include each time we achieve better accuracy. And we should at the end also save the model as well. The best, highest accuracy model, I mean. Okay, let's let this run. And as you know, in neural networks, there are all these connections between neurons, which are just weights, just numbers. And at the end of a forward pass, the loss is calculated by the difference between the ground truth and the predicted result. And we perform gradient descent and back propagation using calculus's chain rule to adjust each one of these weights by a tiny amount, and hoping that system will converge to an actual solution. But here we are actually going to optimize it using completely random numbers. I think it is an interesting exercise because this will actually converge. I have actually done this before, and 5,000 iterations. So this you don't even need this many neurons. Let's just try 2 neurons each. And training data set is 100. That should still be all right. Let's run this when you first. Okay, here we go. See, we are achieving 40. We are already, so this is running very fast because we are only running a forward pass, and we have already achieved 44% accuracy at iteration 296. It's still running in the background. We are just choosing random weights, so obviously. So the best accuracy was 44%, and we also saved the model. Let's now actually use 1,000 items for our data set and run it again. And then we can also increase the hidden layers. So, when we run 1,000, of course, it's going to take much longer. And also the convergence is going to actually be affected. Yeah, this is something I noticed. I built this before because when you calculate yeah, it is still converging, but obviously it's taken longer, and it's taken longer to converge. So for this to converge, we want to use a smaller data set because the mean average error or whatever this system is calculating is going to vary wildly from example to example. So the accuracy is going to remain low. And there is no real algorithm. So each iteration is completely random, as you can see. But it is interesting to see that this is actually converging. Nevertheless, let's increase the neurons to 3 for each layer and run this again. We're training the data set low, but you already can see, look at this, we are already at 72%. But you can see the problem with this approach because as your training data set increases, your compute or the time required to converge is also going to just increase incredibly. So we can also ask it to actually do some test examples at the end. Please perform 5 example tests at the end so we can see the results. We can actually, once Haiku actually gets the project going in a decent fashion, we can actually switch to Cheetah. Cheetah can make mistakes to begin with, but um, at the end, if there's a good code base, then it should actually continue it just fine. Let's reduce the max iterations to 2,000. And let's see what happens. And then we'll add an evolutionary structure on top of this. So if you're already at 50% accuracy. Okay, so we trained it for 2,000 iterations. We achieved 56%. And if you look at the results, um, they are pretty bad. Let's run this for 5,000 iterations and let's test it. Okay, But again, like we are actually each one of these iterations is a totally random situation. So let's change this actually. Can you please write another script where we are actually keeping track of the latest best performing weights and continue from there to this system? That make this a new script. Okay, so if you run this, we didn't even mention any evolutionary or genetic algorithm or something like that. But if you look at its thought, it actually thinks it's a hill climbing algorithm. Last time I did this, well, this is a bit of like a evolutionary algorithm because we are keeping the best performing ones, right? So this didn't perform well. Look, this was actually low at 38%. So obviously your mileage is going to vary. Let's actually reduce the neuron sizes to two because the more neurons you have, the more variability or this random picking situation is going to be. This is an addition problem. It's very simple. So just four neurons, I think, is plenty for this. Our other our other script is actually built. Yeah, see, it's again didn't perform very well. Let's run this for 10,000 iterations. And let's also run our adaptive system as well to the side so we can see. By the way, the code files for this will be available at my Patreon, depending on where you're watching this from. You'll be able to see. You'll be able to see the link in the description or in the comment. I think we accidentally run the other one here. We want to run the random here, 10,000, and run the adaptive one here, Python, neural network adaptive. So here we are already up to 64%. Look how fast we are climbing. We are already at 54%, but the neuron count was at 3. But the climbing to 54% actually took 361. So it didn't actually made a huge difference from here. Yeah, so this is obviously not learning very well, but we can increase. Let's just go wild and increase the max iterations to 50,000. And our adaptive system didn't perform very well as well. Let's reduce. Maybe our training data set is not sufficient. Let's say 200 and run this adaptive on 200 examples. Oh, I am running the adaptive on so I'm mixing them up. Let's put this 50,000 and increase the training data size to 100 here as well. So I'm pretty sure that increasing the training data size is actually going to hurt us. But let's run it again because this has been running for a while and we are still stuck at 43% with just the initial script. Let's run it with 1,000 data set size. Actually, it got there pretty quickly. Well, maybe we did need a larger data set. But I did notice that increasing the data set actually might hurt the performance because the variability in the results is too high. Yeah, I'm not 100% sure. So let's actually run the adaptive system with 1,000 data set size as well. Oh, also, we of course need to double check all of these. This is what I do. Is the adaptive script implemented correctly? Double check and report back. So we're just asking Cloud 4.5 Sonnet here. So this was about it. I just wanted to show you this, that even just by picking the weights in a neural network randomly, you can actually optimize it and you can implement additional structures on it. Look at this. We are actually up to 95% on the adaptive system. But, our iterations are going so much slower due to the training size. But we were able to achieve 95.7%. So that's pretty significant. And here, the adaptive script, it says correctly implemented. I double check usually with 4.5 Sonnet and also with uh, Codex. Okay, so I think you got the idea. I just wanted to share this with you that you can build a network and optimize its weights just with a forward pass. I think that you can actually experiment with interesting ideas. The reason is, interesting ideas such as this, because the brain actually doesn't use back propagation. Of course, you're not going to be able to solve that problem with this simple script, but it's always interesting to consider, useful to consider different points of views and interesting ideas. Hope you found this useful. Like I said, depending on where you're watching this from, the link to my Patreon will be in the description and the comment. If you and there will be more interesting source code or project source code there, and also exclusive videos. Um, Thank you, and see you in the next video.